All right, as we talked about in the previous video, example 1 and the introduction to this section on power series, theorem 1, we talk about the radius of convergence. The radius of convergence, we'll denote this with a capital R. It is a non-negative number, so this means it is 0 or larger, and we are also going to allow for it being infinite. So R can also be equal to infinity. If R is a finite number, then the power series F converges absolutely whenever we consider values of x that are at most a distance r away from the center. Strictly less than that. True, actually, less than that. And then it would diverge if we are more than that value away. What actually happens at the endpoints? So the center of our power series plus the radius of convergence or minus the radius of convergence, that will depend on the form the series takes when you substitute in those values. So it's best to visualize this as a number line here. Here's our real number line. And then at some location, we have our value c, the center of our power series. Now, the radius of convergence, r, if it's either infinity or it is a finite number. So if it's a finite number, then let's say this distance is right here. So from the center, we can either go a distance r to the left or a distance r to the right. Oops. So somewhere right here to x equals c plus our radius of convergence, and over here to x equals c minus our radius of convergence. So everywhere in between, we have convergence. Everywhere in between. Now, what actually happens at the endpoints? So do we actually have convergence of the power series when x is equal to c minus r? And do we have convergence when x is equal to c plus r? That will depend. That has to be checked manually. But you definitely have convergence everywhere on the interior here. Now, if the radius of convergence is infinite, then you can just imagine extending this line in both directions, in which case there is no question about what happens at the endpoints, because the endpoints would be in plus or minus infinity themselves, and you can't actually get there. So you don't have to check the endpoints. You just know that if your radius of convergence is infinite, then your power series converges over the entire real number line. It converges absolutely for all x. Okay, let's go ahead and get started with example 2. Determine the radius and the interval of convergence for the given power series. Now, in the previous video, we talked a little bit about the interval of convergence. The interval of convergence is going to be presented in interval notation, but it is really a range of values of x. You're listing all the values of x at which the power series converges. So in this example up here, our interval of convergence I is some subset or proper subset, we're allowing for that, to be somewhere between c minus r and c plus r. Now, the true interval of convergence I may be excluding both endpoints, or maybe we include one and not the other, vice versa. So that's why I'm saying the interval of convergence is definitely some subset of this. It has the same measure, the same size of it, the length of the interval is the same. We just don't know if the convergence is maintained at both or one of the endpoints. We'll go through this here. So example 2. And whenever we're doing an interval or radius of convergence problem, ratio test. Pretty much ratio test. There are some examples where the root test might be better, but 9 out of 10 times the ratio test is where you want to begin. So we'll let our a sub n be square root of n x to the n. So then a sub n plus 1 will be the root of n plus 1 x to the n plus 1. So then this ratio here, rho, is the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Now, since our series terms are already positive, the absolute value is redundant. It's unnecessary. We don't need it. So we'll just divide these. Root n plus 1 x to the n plus 1 all over root n x to the n. So notice here that we can rewrite our x to the n plus 1 as x to the n times x, in which case the x to the n's would cancel and be left over with just this x. And since this x, the absolute value actually does matter on the x. I should have taken my time there. Because these terms here are positive, we don't need the absolute value. But this x value could be negative. There's nothing in this expression that says we can't plug in negative values for x. So the absolute values bars do have to remain on this x that we'll have. So this will be the limit as n goes to infinity of, I guess I really just need one square root, times the absolute value of x. Now, it's not necessary to do this, but because this is a limit as n goes to infinity, and this absolute value of x term doesn't have any n's embedded within it, we are free to factor or pull that out, and then just take the limit of this expression. Sometimes it's useful because maybe your limit looks a little bit complicated, and if you can simplify things, that helps. So that's just one thing you can do, not necessary. So the limit of this expression is going to be 1 by dominating terms. So 1 times the absolute value of x is the absolute value of x. So we have rho is the absolute value of x. Now we know for the ratio test, if rho is strictly less than 1, then we have absolute convergence. So we really want this absolute convergence. So we are going to require that rho be strictly less than 1. This implies that the absolute value of x, since that's what rho is equal to, that is less than 1. So right here, notice that our center of our power series, this is not x minus something to the n, this is x to the n. Well, this means our center must be 0. So again, this we can view it as the absolute value of x, but we can also interpret this as x minus 0 in absolute value. So this really is that term we're looking for. So whenever you have your center solved for, we want to get it in this form. Once you have it in that form, this number right here, that is the radius of convergence. So the radius of convergence is 1. Okay? All right, so now that we know what the radius of convergence is, we really want to know what happens at those endpoints. So our center of the power series is 0, our radius of convergence is 1, so we've got these values x equals minus 1 and x equals positive 1, where we need to figure out what does the series do. Does it converge? Does it diverge? So in order to do this, we want to check the endpoints manually. So we can plug in -1 into our power series? Well, if we plug in -1 into this expression, we have the series of -1 to the n. Oops, sorry. Why did I write that? Oh, no, that's correct. Yep. Times the square root of n. So this is an alternating series. But keep in mind that although it's an alternating series, the alternating series test only shows convergence. It doesn't help you show divergence. This series term, if we look at the sequence term, -1 to the n, root n, this limit here does not exist, and therefore by the divergence test, this series here diverges. So we actually have divergence at the endpoint. So we are not going to include -1. We're going to leave that as an open circle. So I'll shade the rest of this in, and we need to now do the right endpoint. So when x is equal to +1, we obtain the series root n. And the limit as n goes to infinity of root n is equal to infinity, which is not 0. Therefore, we have this series diverges by the divergence test. So again, we'll exclude that right endpoint. So this tells us that the interval of convergence, I, the interval of convergence, is equal to the open interval from -1 to 1. It is open in that we're using parentheses, which symbolize or indicate that we are excluding -1 and 1 from that interval. It's every x value strictly greater than -1 and strictly less than 1. So that is our interval of convergence. All right.